Hey y'all, it's Miss Johnson. Today we are talking about optimizing functions using calculus. And the process we found in class was to have an equation that you want to optimize. So have an equation you want to optimize, which just means finding the minimums and maximums. Take its derivative to get the slope equation, right? Set that equal to 0 and solve for what you're solving for, right? Solve for x or whatever the variable is. And that tells you the x values of the critical points. And then you got to check your thing, like, do you want the actual x value? Do you want the y value? Whatever. I'm actually going to put this. That was a good thing to write. So I'm going to put this at the top of our notes. Boom, boom. So again, one more time, the process is figure out what you're trying to optimize. Take the derivative of that function, set that derivative equal to 0, solve for x. Easy peasy, lemon squeezy. Let's see how it goes. All right, so these 3 questions that I'm going to do on the video are pretty much rewrites of the ones on the worksheet. So watch the video, watch the first question, pause it, do the first question on this worksheet, right? Play the video, watch the second question, pause it, do the second question. That's going to be the best way to do this assignment. Let's get it. All right, let's find out what are the dimensions, the maximum sized rectangular luggage that can fit in an overhead baggage compartment on an airplane, which is modeled by this equation. So I don't know if you all have ever been on an airplane, but when you go to put your backpack over top of the seats, there's this half circle, quarter circle baggage compartment almost. And we want to say we've got a piece of luggage that's a square or a rectangle, and we want to shove it in this compartment. And we want the biggest one possible, right? So we could have done this. We could have had a rectangle that looks like this, that's corner is actually on the function. This light blue one is much smaller, of course, so we hate that. This purple one is smaller than the dark blue one, so we hate that. We're trying to find the biggest possible one. So when we go to our have an equation you want to optimize, the equation is not the equation for the baggage, it's the equation of the area of this baggage, right? The height here of this square package or rectangular package is our equation. So if it's length times width or height times base, that's our height. And this distance is just how far x you go. So this distance is x. So base times height is going to be x times negative 2x plus 30. So our area equation we're going to distribute the x, is actually going to be this. And this is what we want to maximize. Want to maximize. We'll call it that. We found our equation. Now we're going to take the derivative. To take the derivative of this, we use the power rule. So have our equation, take the derivative. Now we're going to set this equal to 0 and solve. We're going to move the 30 to the other side. We're going to divide by negative 6. And then we're going to say, what's the square root of 5? It's like 2.36. We're done. Psych. We should figure out what the question's actually asking for. The question asked for what are the dimensions. That means length and width. Over here, we found the width. We still need to find the length or the height. And half of our equation done. But over here, blue, we want to plug that number into this y so we can figure out what the actual height is as well. So off to the side, we're going to say y is negative 2.36 squared plus 30. This number squared is 5. That's how we got it in the first place. That's -10, and that is 20. So here are our dimensions. X is equal to 2.36, and y is equal to 20. We have successfully found the dimensions that maximize the area, or the area of the luggage. Yeah. You can play that in 0.7 times speed if you want. You can rewatch it, but that's how the first question is going to go. So go ahead and try that first question now. Welcome back. I'm pretending that y'all actually paused. Here is something that looks like the second question. Next up, we're going to find the area of the biggest rectangular window that has a perimeter of 64 meters. Huge window. Truly massive. The biggest meaning we want to maximize the area. Okay, so we're going to find an equation. If we want to maximize area, we have to find an area equation. That's just x times y. And now we say, let's take the derivative. Oh, this is some sirens going off. How do we take the derivative of something with x and y? We don't, right? Off to the side, we now have a goal of make the area equation only x's, right? I'm not comfortable right now taking this derivative. So let's think, do we have any other information that we could use to put y in terms of x? The answer is definitely yes, right? If our perimeter is 64 meters, and we also know that the perimeter of this window is 2x times 2y, or plus 2y, right? We can then say, let's solve for y and then replace it in this equation. So I'm going to divide both sides by 2. I'm going to get 32 equals x plus y, and then I'm going to subtract x from both sides and get that y is 32 minus x. The reason I'm going to do this is I'm going to rewrite this. Now the area is x times 32 minus x. Pretty good. I'm going to simplify it by distributing. And now this is something I can take the derivative of. I'll do that now. Beautiful. Then I'll set that equal to 0, as is my process for maximizing things. I'll move the 2x over. I'll divide both sides by 2 and get that x is 16. I'm done. Psych. I now need to figure out what the question was asking for. Find the area. That's what the question was asking for. That's totally fine. I have an area equation. I have the x that makes me maximum. So I will plug that into my area equation. And then do that real quick. 32 times 16 minus 16 times 16. That makes sense. And we'll get 256 meters squared is the final area. That is the maximum version of this area. You might say, Miss Johnson, what does y equal though? What's the base? It doesn't matter for this question, but it happens to be 16. Fun fact, when you maximize rectangles, they're always going to look like squares. Unless there's like odd constraints on something that needs to happen. Nice. And then, so pause this, go do the window problem. Welcome back. Finally, let's go to the horse races. Let's go to the Kentucky Derby. The Kentucky Derby is a 1 1/4 mile race, which means it is 6,600 feet long that these horses have to run. And the Derby people are looking to shake things up. They want to redesign the course. Right now, it looks like kind of like the straights, and then you run the curvy part, and then it's a straight, and then you run the curvy part. And they want to say, okay, we still want it to be 1 1/4 miles long, but we're looking to shake things up so that we can maximize the area inside of the track. So let's do that for them. If we want to maximize area, we need an area equation. The area equation for this one's kind of weird. The area equation for this one is going to be this rectangle, which is 2r times x, plus these two half circles, which together make one circle, and the area of the circle is just pi r squared. Cool, we've got our equation. Let's take our derivative. Oh no, right? We don't want r's and x's. We only want either all r's or all x's. So off to the side, we do our side work, and we say, okay, we were told that the perimeter is 6600. We also can look and see that the perimeter is x plus half this circle plus another x plus the other half of the circle. So it's going to be 2x's plus 2 pi r, which is the perimeter of a circle, the circumference of a circle. And then I'm going to solve, I'm going to divide both sides by 2. And then I'm going to, I'll solve for r. No, I'll solve for x. Right, I subtracted the pi r to get x by itself. And now, when I rewrite my area equation, every time I see x, I will instead write 3300 minus pi r. And now I'm just going to keep simplifying this. I'm not doing any derivatives yet. I'm just using algebra 1 and simplifying these things. So I distributed the 2r and got 6600r minus 2 pi r squared. And then I did 2 pi r squared plus 1 pi r squared is negative 1 pi r squared, which is where I got this. And now I've got something with only r's. I'm going to take the derivative. Just some normal power rule stuff. And then once I've taken the derivative, I set it equal to 0. I solve 6600 equals 2 pi r. R equals 6600 divided by 2 pi. 6600 divided by parentheses 2 pi parentheses is 1050.42, let's say. B. We're done. Psych. We have to look what the question is actually asking. The question is saying find the straights and radius length. We found the radius. So let's come down here. We're doing good. And then to find the straights, so that's the x, right? Instead of plugging it into this area equation, because that would give us the area, not the x, we're going to plug it into this equation. If we're looking for x, we should find the equation that equals x, right? So off to the side here, we're going to say, what is x when I plug in 1050.42? And if you do the calculations, you get x equals 0. You say, Miss Johnson, surely that's not right. And I'd say, don't call me Shirley. It is right. When you maximize the area, it turns out that it's just going to be a circle with circumference 6600. Right? The circle is a very efficient use of space. So whenever we're maximizing areas, circles come out a lot and squares come out a lot. All right, I think you're good. I think you're good to do the third horse track problem as well. As always, if this is confusing, rewatch the video, ask your friends, email me, come to office hours. The worst thing you can do is sit at home and be stressed about math. So reach out to me, reach out to your friends, reach out to the internet, and we will get through this together. All right, y'all. I'll see you on Tuesday.